All right, we got a few energy conservation examples to do here. There's 4 of them. They've got a couple of different ideas, but one of them's pretty cool. So let's get to it. Not all these are actually full energy conservation, but we'll get to that. So first thing here, all right, we've got a 2 kilogram object in the positive x direction. Experiences a force shown in the graph. What is the maximum speed the object experiences if it starts at the origin and at rest? Okay, so first off, you could sort of do this, right, with acceleration a little bit, okay, but not. It's easier to do it with energy. So first off, right, we got this force, we've got versus position, and the first thing we should know is that this is the point of max speed. Right, positive force is going to accelerate it, and then as soon as it reaches there, it's going to start slowing down. So I want to get from 0 to 6. And probably the best way to do this, right, is to think of work is equal to change in kinetic energy. Right, and work is also equal to the integral of f dot dx. Okay, now, best part of this, right, integrals also be the area under curve, right? So there into this curve, we've got this box, 3 boxes, and then 2 half boxes. So, and each box is 2 by 2, right? So it's 4 boxes each of an area of 4. So work equals 16 joules. All right, so the work is equal to 16 joules. That means the change in kinetic energy is also equal to 16 joules. So change in kinetic energy, and that's kinetic energy final minus kinetic energy initial equals 16 joules. Kinetic energy initial, this is 0, right? Because we initially said it starts at rest, right? It starts at rest. So I have 1/2 mv final squared is equal to 16. 0. This is 1/2 times 2. V final squared equals 16, and V final equals 4. And since that's the V final at 6 seconds, this is the maximum speed. Our second example, we have an object starts at rest, again, experiencing a force of 5I plus 4J. Right, so this is vector notation of the force. And during that time, it moves from an object. It moves from the origin to negative. It's be a little bit easier to read if that into the negative 3I plus 7J. So this is its position. So what is the work done by this force? So we'll start with the first one there. So we do have, right? This we know that work is right. It's equal to the force, inner force F dot dx. Actually, really, honestly, I should probably stop calling this dx. That's in one direction. This is ds. ds is a path, like this displacement, in any direction. Okay, so I don't really want to call it dx because obviously this is going into I and j direction. So first off, this converts to, or is equal to force dot f dot s if, right, if f is constant. And the force is constant, so we can do this. And because we're in vector format, right, f dot s is equal to fi times, right, or actually really, we can just say that times x, the x, right, or actually, well, we'll say si plus fj times sj. And we have those. This is equal to negative 15 plus 28. So 13 joules. The work done is of 13 joules. So, but the object has a velocity of 2 meters at that point. So what is the explanation for that? Okay. So first of all, let's say that. So work is equal to change in kinetic energy. And the kinetic energy is kinetic energy final minus kinetic energy initial. So that's 1/2 times 3 times 2 squared minus 0. And this is 6 joules. So how can this work be equal to 6 joules, but this is only work of 13 joules? It doesn't make sense. Except this right here This is the net work. And this right here, this is the work of our, this work right here, this is the work just of our force, of that particular force. So basically the explanation is there's another force, or more than one force, another force, or more than one, does, right, -7 joules of work. Okay? Right? Because net work, right, is going to be equal to 6, which is equal to work 1 plus work 2. Let's keep going. So this work 2 has to be at least -7, or maybe there's more than one that at -7. All right, this is the cool one here. Why aren't roller coaster loops circular? So you look at this right here. See this loop, right? This loop is not a circle. It's like this teardrop. Right? Why is this not a circle? Why isn't the loop like that? Why isn't it more circular? There's actually a very good reason for that. So let's examine why. All right, so let's pretend it is circular. Okay, so we have a circular loop. So again, it's like coming in, going down, and then we get flat, and it goes basically in a circle. Full circle, right? So this is 5 meters, and we say it's going at 10 meters per second at the top of the loop. Okay, so I want to know what the speed is at the bottom of the loop. What is the apparent weight at the bottom of the loop? Now, to get apparent weight, I need to know about all the forces at the bottom loop, and because it's going kind of in a circle, okay, I need to at the very bottom know what the speed is. So that's easy to do. I can do conservation of energy, right? So there's energy initial, right? Kinetic energy initial plus potential energy initial plus non-conservative work is equal to kinetic energy final plus potential energy final. Okay, right? I don't need any more there. So if I'm doing that, right, one of the things here is that we can safely say there's not much friction. There's a little bit, but let's say there's not much. Let's just try and get rid of that as much as we can. So not much friction. Kinetic energy initial, this is, let's say this is at the top here. So this is 1/2 times mass times 10 squared. Potential energy initial, right, is going to be, again, that height here. Let's say I'm going to make this spot right here. This is h equals 0. So at the top, it's 10 meters tall. So that's m times 9.8 times 10. And this is equal to 1/2 m v squared, this is the velocity at the bottom, plus the potential energy final is 0. So I get, this is 50 m plus 98 m equals 1/2 m v squared. Okay, we can cancel out the m's, right? So I get 148 times 2 equals v squared. This is equal to 296. All right. Now I could solve for v here. I can take the square root of that, but I'm actually not, and we'll see why in a second. So now I'm at the bottom. My card is at the bottom of the slope, right? Or at the very bottom of the loop. Okay. So what are my forces acting on it? All right. So we've got Fg and the normal force. And the normal force is best related to the apparent weight. So I want to know what this normal force is. But I also know this is basically going in a circle here. So I can say F net equals Fn minus Fg. But F net is also equal to mv squared over r. And that's why I didn't bother to take the square root of it. It's equal to Fn minus, this is 9.8 times the mass. So this right here, this is m times 296 over 5 equals Fn minus 9.8 times the m. I do this, right? This is, and it comes out to be that Fn is equal to about, I think it works out to be, oops, that's right, 69 m, which is about approximately 7 g's, or 7 times the force of gravity, 7 mg. 7 times the force of gravity. It's not good. 7 times the force of gravity is enough to make people pass out. Right? Not everybody, but definitely some people will pass out on this. So, I'm going to actually make a new slide here. So why does that mean they do it like those teardrops? So let's say we have the same loop, but now it's a teardrop loop. So it's like this. That's exaggerated, but what we have here, right, this is still 10 meters. Okay, right? Now, the top here, we're going to say this part right here, if we split this in half, this is like a circle of radius 5. But if I'm going at this point right here, right, this is also a circle, but this circle has a radius of, say, 20 meters. Okay? Now, the good thing is that this whole part here, if I was to select, this whole part is still true. Right? The height's still the same, the velocity at the top's still the same. But now when we actually do the force diagram, we get a very different result. It's still Fg, Fn, but now we do Fnet equals Fn minus Fg. This Fnet is m v squared over r equals Fn Fg. Oops, that's a 9.8 times the mass. This right here, again, v squared, but this time it's over 20. So we got 296 m over 20 equals Fn minus 9.8 m. And this comes out to be that normal force is equal to about 24.6 mass. This is about 2.5 mg. Okay, by stretching out this bottom part, all right, we reduce that by a factor of essentially, well, not quite 4 because it went from about 7 to 2.5, right? Because we set this factor, but we reduce it by a fair bit. Okay, this everyone's going to survive. So they literally do this. They literally make it so you can have a reasonable speed at the top, but not pass out at the bottom. So they actually make the teardrops that way. Now this is going to take me on another thing. Like, why do we only do at the very bottom and very top? Why do we only consider the centripetal force at those points? Why don't I do it at like the side? And here's the reason why. So let's go back to a circular loop, right? We got it coming through like this. Why don't I ever consider this point right here? Well, let's look at this. If we look at that point, we've got Fg, we've got normal force. And the problem with this is that the net force is supposed to be that way. So what am I doing with this Fg force here? All right? Well, it doesn't really work. Fc can't be towards the middle if Fg is down. And the reason this means is that we don't have a situation where Fc actually applies. Fc assumes it's constant velocity. But as it's going up through this curve, right here at this point, this velocity is not constant. It's constant right when it reaches that top point and right when it reaches the bottom point. So those are the 2 points we pay attention to with these problems. All right, last one here. We've got a bottle cap sliding down a 1 meter tall slide. I use one a lot here. But basically, we've got this slide that's a meter tall, and it's on a table, and then it's going to arc out and it's going to land 1 meter away. And the question is, how much non-conservative work was done on the bottle cap as it goes through this path? There's our bottle cap. It's going to go, right, it's going to go like this, and then down like that. Okay? So, first off, notice, why is this curved? Well, it's the only way to have it curved is to have it like go down and then go off like that. So you can't really do it with force. Curved arc like this, right? Force isn't going to be constant. It's tough to do it. But that's why we have energy conservation. Okay, so but this is basically a two-part problem. We've got this free fall projectile motion part and this slide part. So we got slide. Okay, and when you got the slide, you want to do especially a curved slide. You're gonna do it with energy conservation. So we got kinetic energy initial plus potential energy initial plus non-conservative work equals kinetic energy final plus potential energy final. Then we got part 2, which is this projectile. To do that, we're going to do some 2D kinematics, right? So we've got change in x, change in y, initial x, final x, ax, time. Okay. Change in x is 1, change in y is -1. The initial y is 0, right? It's coming off horizontally. Ay is -9.8. All right, and here I have, and so I guess I skipped a couple steps here, figuring out because I already know how we're gonna do this. But basically, the idea here, right, is what connects these two, right? The final velocity of this is the initial velocity of this here, all right? And I don't have enough information to solve this part, but I do have enough information to solve it here. So I can solve for time with y. So -1 equals, use the change in y equals v initial times time plus 1/2 at squared thing. So this is 0 times time minus 1/2 times, or actually it's plus 1/2 times -9.8 times t squared. This goes 1/4.9 equals t squared. T equals 0.45 seconds, basically. And then I can do that in the change in x, right? Oh, because ax is 0. That's the other one I know. Right, so change in x equals v initial x times time plus 0. And we get that v initial x equals 2.22. So I can go plug this in here. So I have 1/2 m v initial squared plus m g h plus non-conservative work equals 1/2 m v final squared plus height initial mgh final. Now for height, I can make this height final equal to 1 and height initial equal to 2. I could do that, but as we talked about, it doesn't matter, everything's relative, right? So I'm actually going to make height, I'm going to undo that, and I'm going to make height final, actually let me do it here. Height initial is going to be 1, I'm going to make height final 0. Make my life slightly easier because that means this height final is going to be 0 here. So I've got 1/2. Oh, and this is 0 too. I guess I should. This is 0, and this is 0. So now I've got 0.01 times 9.8 times 1 plus non-conservative work equals 1/2 times 0.01 times 2.22 squared. When I do this all out, I get non-conservative work to be, I don't know, -0.0738, -0.038 joules. Okay, and that likely is the non-conservative work of friction. All right, there we go.